Всем привет! Сегодня я расскажу о том, как мы делали распознавание жестов.
Hello, folks. Today, let me tell you about our experience of the on-device gesture recognition on the SberPortal device. A few words about the device. This is a smart screen with a widescreen cam, high-quality loudspeaker, and high-performance hardware. Speaking about the hardware for the on-device gesture recognition, well, I have to mention that first of all, it has a wide-angle 8-megapixel camera and the M-Logic A311D chipset. It's equipped with a chip that will actually perform all the calculations for the on-device gesture recognition. So the goal was to recognize the static and dynamic gestures. In my talk, I will cover only the static gestures for the sake of time. So we decided to implement the on-device gesture recognition without sending imagery to the cloud. The on-device recognition has a number of benefits. Well, first of all, the user data is not leaked to the cloud. It's 100% private. Plus, it minimizes the delay, because if you start sending data back and forth, the latency would be too high. So we had to recognize those gestures, which are shown in the screen now. You may ask, why do we need that? Well, there may be situations when the users may find it inconvenient to give commands by voice. Like, for example, you can use this V gesture to activate this assistant without saying anything. The mute gesture can be used for muting the video, and like or dislike gesture, thumbs up or thumbs down, can be used for liking or disliking the audio track or movie you are watching. As to the challenges we faced, well, the first challenge was speed, because all the gestures had to be recognized right there on the device. And the second challenge was the very diverse scenarios where the users give their commands by gestures. So we had to predict as many scenarios as possible to make sure that our device would recognize those gestures in all the conditions. So in the first case, picture, you see the user given a V gesture with the palm turned to him. It just turned out that for some users, it's more convenient. In the second case, we see that the proportion between the hand and the face is different from the normal image, and the machine gets a little bit confused. In the third picture, we see a multicolor background, which also makes it more difficult to recognize the image. And in the fourth and fifth images, there's too much backlight for the user, so the machine can hardly see the gesture. And in the fourth image, the camera is located on the floor at a different angle from the normal. So a few words about the chip. It's the M-Logic A311D. It has 3 processing units: the ARM CPU, Mali GPU, and the NPU. That's the guy we're going to talk about now. The NPU can perform 5 tops of 8-bit integer operations, which limits the number of types of calculations we can do. on this device for Quantin? Well, MLogic has its own tools for Quantin, but they're basically a black box. But we know that they use asymmetric Quantin with the calibration data set of about 100 samples. The tools were quite okay. The maximum slump in our networks was 1%, which is quite okay for a production device. The chip has 2 gigabytes of RAM shared with the ARM CPU, which also sets certain restrictions to the type of model we could put there. As to the performance, we measured the performance for different architectures. Core i5 3.7 gigahertz and our NPU. So it turns out that the Intel architecture is much better performing than the NPU, but this is a generic problem for all the NPU manufacturers because they haven't optimized this part of the calculations. So we implemented our own modification of the MobileNet V2, and we see that in our case the inference time is quite comparable, but the MobileNet is much better in terms of quality for a certain number of operations. The most important part of this project was data collection. Well, now first I will tell you about the way we collected the videos where the people making gestures, then how we dealt with the false positives, and in the end I will tell you about the way we dealt with the difficult backgrounds. Well, first of all, as to the data collection, we used the Toloka service. This is a task management service run by Yandex. We ask the users to record a video with a specific gesture and send to us. We gave them a guide on how the gesture should be made, where the user should be located in terms of distance or posture, so as to collect the maximum number of possible cases. After a certain number of iterations, we managed to develop quite a concise guide, very easy to understand for our users, and it enabled us to collect about 100 videos per hour. After that, those videos were checked to remove duplicates, because there's quite a number of those fraudulent users who register several accounts on Toloka and send several results for one and the same task. Then we had to check the correctness of gesture in compliance with our guide. Then we processed the video, we slowed it down, and added the timestamp function, and asked the users to make timestamps where the gesture starts and where it ends. And after that, it was additionally verified by other Toloka users. So in the end, we managed to collect those videos at the rate of 100 videos per hour, and the cost was about $1 per video. But well, clearly we ended up with having many unauthorized gestures, as you can see here in the screen. So in this screen you see the quantitative measure of improving the quality of this model. So we see that the quality ramp up was quite significant. We ran this exercise in several iterations. I have to say a few words about the metric we used, and I will now tell you more about that. Well, clearly, any metric has its limitation. Like, for example, there's a top limit, and the metric cannot reach this top limit because sometimes users make a gesture and it's not quite clear whether the gesture has been completed or not. We tried to filter such videos out, but they still made their way into the training data set. At the next step, we started dealing with the false positives, like, for example, when the model recognizes a gesture which hasn't been actually made. Like, for example, in the first picture, the lady is making a V gesture, but the system recognizes it as the mute gesture. Or in the fourth picture, where the lady is holding something in her hand and the system recognizes it as a gesture. And in the third picture, there was a user with a gesture printed on his T-shirt. And the hard negatives mining, where we ran this model through a large sample of video. Trying to make sure that the model will recognize the false positives from the true positives. So we mined those negatives from the internet, from some of the target services, like, for example, from everyday scenes where people cook or clean the apartment or eat. Another interesting example or interesting source of training data was interviews with the sign language, because clearly lots of signs are being made by the sign language users. We also used talk shows, TikToks, and we mined streams and Zoom conferences. The beauty of Zoom conferences as the source of data is that, well, they take far too long. People are over-zoomed already. And after a certain time into the conference, they start making various gestures, touching their face or moving their hair. And here we observed a very significant improvement of our results. And the first problem we had to deal was the problem of difficult backgrounds. At some point, we realized that the model finds it difficult to recognize gestures made or the multicolor or patterned background. The first way to address this challenge would be to take a model which would segment out the human from the picture and send it to the gesture recognition model. But the problem was that such models, such segmentation problems do not fit our purpose, because when they segment out the human, they tend to cut out the fingers, but whereas fingers play a very important distinctive role in our gesture recognition algorithm. So we used the method which is called matting. So here, let's imagine there's a video frame and the background frame. We send it to the matting algorithm, and the algorithm mats the background. So we will ask the Toloka users to make videos without any gestures, with just the background in, and the second video with the gesture made on this background. So for the matching purpose, for the background matching purpose, we use the World is Your green screen service, which is quite a well-known tool for cutting out the objects from a background. Everything is trained on a synthetic data set, and in the end we get the mask for that. So we tried to run it through those videos we collected through Toloka, and we realized that if we use it out of the box, it has quite a low accuracy, or sometimes the algorithm cuts out the shadow together with the object. So to address this problem, we ask Toloka users not to approach the wall to a certain distance, to keep a certain distance from the wall. And we also added another restrictions to the Toloka users so as to make sure that the picture quality, picture resolution is sufficient. But still we ended up with bad quality images, like for example in the third case where the model segments the clock together with the human object. Then we added different backgrounds to those segmented images and trying to identify the false positives. Like for example, in the first case, we see that the neural network can't differentiate between the palm and the hand. And in the third case, it couldn't segment the gesture from a multicolor patterned background. So, having completed the background matching exercise, we took the accuracy of recognition even further. We understand that many people still put carpets on the walls, and we had to make sure that it doesn't become a problem for the on-device gesture recognition through SberPortal in the production version of the model. As to the model as such, by the way, we use a frame-by-frame model. We make a crop. We use the ResNet 34, and we are also experimenting with the MobileNet NPU. We use all the standard augmentations. We use the ImageNet pre-training. We tried to pre-train using other methods, but there was no significant increase in recognition accuracy. As to the post-edit, we take the window of 9 frames, and to make an additional false positive removal, we require that the angle of the head turning would not be too big, and we ask the users to be static, so neither the face nor the hand move too much. That's it. Thank you. I'd be happy to take your questions. Thank you.